Good morning, everyone. Today, the first lecture will be given by Dr. Tobias Kuna. He will continue on the topic, can we see the forest without losing sight of the trees? Thanks, Tobias, please.
Okay, nice. Everybody, welcome back. And let me just start with, are there any questions? Somebody want to ask any question about something? Okay, so if not, I mean, we just considered yesterday, better to say, we consider the case d equal to 1. So let me now do the case d equal, there's the page gone. The case d equal to 2. So let me remind you what is our problem. So I have given two numbers in this case. So I have M1 and M2. Problem, what is our problem? What we want to do? Our question is, when can one find the probability P on the natural numbers? So we start at n and 0 and goes to R, such that, and so what do we need? So what are the properties? So we have, first of all, that each of the probabilities has to be non-negative. Second, the sum over all probabilities has to be 1. And third, I have, if I look at that's exactly what I mean with being realizable. If I take j to the power k, p of j, then this should be equal to our pre-given numbers, m of k, and we have here exactly 2 of them. That was what I called the truncated Mormon problem on n0. So at the moment this is on I'm here on page 5 in the lecture notes. So if you are following copying it, then you can just use the lecture notes. So let me try to get some necessary conditions. Okay, from last time we saw that, and this is actually inherited to this case, that M1 has to be non-negative. I mean, let me remind you, so this was, the idea was just that J, P of J has to be greater or equal to 0 for all 0 to infinity, because P is non-negative, J is non-negative, so this has to be non-negative. Okay, so let me think about something, what I can say in a necessary condition, the case 2. And now you will see that things becomes already a bit more specific, because I will use a particular ansatz. And it's probably not so clear why this particular ansatz is right. So I just I look at an expression of this form. Okay, so let us let us analyze this. So if I have here the real number line, and then I have here the integers. So let's say 0 and so on. So then I have here L, and then I have here L plus 1 and further on. So L plus 1 is, sorry, this is L plus 1 is this one here. Then if I write the polynomial associated to it, so if I plot the function x minus L, x minus L minus 1, then how this function will look like, it will have a 0 at L, it will have a 0 at L plus 1, and then if you look for the sign, you will see that it has, oops, that it has to look somehow like that. Okay, it's a bit, the painting is not the best, but I think you understand which is the idea. So, and then we see that this is actually non-negative on all integers, on all integers, and in particular on all non-negative integers. So I forgot to multiply here with P of J. So this is non-negative, this product is non-negative. So everything is non-negative. Okay, so let me rewrite the left-hand side. So if I have to multiply these things out, and now comes another trick. So what I do, I smuggle an M1 in. So we'll see in a minute why this is a good idea. At the moment, it makes things only messier. So J minus M1 minus L minus 1. Okay, now I multiply that out. Okay. So first I take this one with this one. I forgot the P of J, obviously, every time we multiply this. So I take this with this one, so I get J minus M1 square P of J. So that are the terms which goes with a square. So next terms, which I will have a look at, is J equals 0 to infinity, the one which have only a first power of J minus Mj. So I have this one multiplied with that part. So I get here a minus L minus 1, and I have this part multiplied with that one. Sorry, I forgot. I made a mistake. Okay. So where it is? I made a mistake here. So I have to correct for what I subtracted. So I have here to make plus M1 minus L minus 1. Not to that these two here are constant, compensating each other. So I get here another plus M1. So that's what comes from here. And then, I don't know, from this double wiggle, I get another plus M1 minus L. That is a double wiggle. And then the last term is this one with that one. So I get plus M1 minus L times M1 minus L minus 1. So I get here once the double wiggle, sorry, the double wiggle and the wiggle. Okay. So let us concentrate. So I have not enough space. So let us concentrate on this term first. Here. Okay, so actually I can put the bracket out. So I get here some kind of whatever it is, I don't care. And then I get here's a sum j equals 0 to infinity j minus m1. All the other factors doesn't depend on j, so I can put them out. Okay, but what I get here, that because the sum multiplied with p of j, I forgot the p of j. And here I also forgot the p of j. So, and here, okay, I was too quick. So here actually I have another factor. So this is a sum. I have also this sum p of j equal 1, 0 to infinity, but this is just 1. So this factor actually disappeared. So it doesn't appear there. I dropped this one mentally. I have done this kind of calculation 5,000 times in my life, and so I just do them in the sleep, and I forgot to tell this. Okay, so here I use that the probability is 1. Here I still have this factor. Now, but if I look at this, yeah, I mean, this one and this one together is give me just m1 again, yeah? And the m1 doesn't depend on j, so I get 1. Okay, let me write that. So for the people who are not so used to probability, this may be more difficult than, I mean, you don't see it immediately. I mean, probably if you sit down for a few minutes, you will see that. So you get m1, and then you get the sum j equals 0 to infinity p of j. So this bracket, and then you see that that is nothing else. This thing here is a beautiful 0. Yeah? So all of this disappeared. Okay, so let me insert a new page. Why it doesn't make it? Okay. So let me just copy what we had before. So what we remain with is, so I just copy so you don't, there's nothing to be lost. So we get here j minus m1 squared p of j plus m1 minus l times m1 minus l minus 1. Okay, and so the first one here I can also rewrite. I don't do the calculation. If you have ever had a probability course, you have done this millions of times. This is just the variance. So this is nothing. What is doing? So this is nothing else than m2 minus m1 and all of that square. Okay, and what I see in this term, it's again the polynomial which I have before, and so I see this is non-negative if if m1 is not an element of the interval l plus 1, because that's the only place where this polynomial is negative. So, but what we have, so let me recapitulate. So I arrived at this formula. So I get I get the following condition. I get from before what I derived before. I get that this has to be greater equal to 0. No, that's where we start from. That is coming from here. I know the other side has to be greater equal to 0. Now I made the recalculation of this side. So my condition is that for all L, that this has to hold. This has to hold for all L. No, because for any L, I can do this calculation. For only L, which is a natural number, that's the only thing I used about L. And then I notice that this is non-negative if M1 is not an L plus 1, but it's negative if I'm inside. So if among these conditions I see the left-hand side doesn't depend on L, this thing doesn't here depend on L, it has to be true for any L, so I will try to choose the L which gives me the strongest condition. This has to be positive or non-negative, so the strongest condition is if I make this expression here in this bracket here as small as possible. And the best choice is that L is such that M1 is in this interval. Yeah, because then this thing becomes negative. Otherwise, it's always positive. So this must be the minimal value. So the best choice is L such that L is less or equal to M1, and this is less or equal to L plus 1. And so we get so summarizing, so what we get the following. We get the following condition. We get the condition that M2 minus M1 squared, which is a variance, is greater or equal. And now I can write this as theta times 1 minus theta, where what is theta? So theta is defined as false. So theta is the theta of M1, or for short, I just say theta is defined as the following thing. I take M1 and I subtract the floor of M1. So what is the floor? The floor, this is the largest integer less or equal to M1. Or another way of saying it, another way of seeing is I write M1 as the part which is before the dot, which is that, plus the things which become after the dot if I write it in a decimal kind of expression. And so what we see here is we see the surprising thing that not only the variance is non-negative, everybody knows that the variance is non-negative, but in this case, you have to have more. You need that it also has to be larger than this kind of theta. The theta, I need this later on, I should stress this, is between 0 and 1. So that means that this is actually in 0 1/4. If I didn't make a mistake. But you can easily check where it has its minimum. Okay, so we got a necessary condition. So we have two necessary conditions. We have the condition that M1 has to be non-negative and that this condition has to be fulfilled. And I forgot to say, that's something I want to say. This thing has a name, obviously. This is what is called Yamada condition, was discovered in 1963. In a much more complicated context. They were interested actually in liquids and the things, and they just discovered this as a byproduct. They never synthesized it in a way like I did it here. So please put any questions in the chat, or if you want, you can also ask a question. So this is a necessary condition. Now the question is, what is with sufficient? Before I go there, I should maybe make another comment. You saw here, when I started here, this thing here came out of the blue. Yeah, this fell from the sky, and I said, yeah, that's a great idea, yeah. And then I started to subtracting the M1 here, and yeah, that's another great idea, which essentially fell from the sky. Okay, that's good. I mean, this is a correct solution. I can do that. The problem with this is, okay, now you ask me, okay, but what is with d equal to 3? And then I can try to do the same trick, and it will actually work. And then the next question you will ask me, okay, but what is actually with d equal to 4? And then you will very quickly recognize that, I mean, you're not very quickly, we were somehow the first one probably who properly recognized that this trick is not working anymore. So we went on this journey actually starting from this general liquid theory we were interested in, and said, okay, what was the easiest question we could try to consider? And this was the easiest question we could come up with. And so we thought, okay, this Yamada condition we actually already knew because we found that in the literature already. So we know that. And so now we try to understand this a bit better. We understood this in this kind of easy case, so we're very happy. Then we said, okay, let's do d equal to 3. Take us a few weeks, we could do that. Okay, let's do d equal to 4, or better to say, we just said first, okay, let's look in the books. Somewhere in the literature, somebody must have done this. It was very moment problems on the real line was a hot topic in the 40s. So there are tons and tons of books. I mean, piles. I mean, it's very connected with the orthogonal polynomials, continuous fractions, complex analysis. There's a lot of literature written about it. And so we said, okay, that's the natural case. Somebody must have come up with this idea before us. So we spent some time reading through hundreds and hundreds of pages of books trying to find it, and we didn't find anything. And then we said, okay, well, we do it ourselves. And then doing the case d equal to 4, we understood why we didn't find anything, because the tricks don't work. Yeah, what you find in the literature doesn't work. And then it took us on a long journey to actually crack this. And I'm not able to arrive at the total end of the story, but I will give you some idea how we get some way into that. But before I do that, I want to show that also in the sufficiency, somehow the situation is even worse. So one way of solving the sufficiency is a constructive one, and that is find P. Yeah. If I can find P explicitly, I showed my conditions are sufficient. So okay, here I have the problem of too much choice. Okay, but I can, maybe I'm just stupid, and I try something. And I do something like that. And I do the same thing which I did before. I choose L, which I did exactly. This is what I did in the case in one dimension. I choose L like that. And without loss of generality, I assume that R is neither L or L plus 1, because if it would be L or L plus 1, I could just absorb it in the other coefficients. So that would be nothing new. Okay. Now what we end up, we get 3 equations, but unfortunately we see very quickly that we run into some kind of rigidity problem. So there's a problem. So things are not as smoothly sailing as in the one-dimensional case. So assume we are in the case. I just try to show you that we have a problem. So I left for you as an exercise to do that yourself explicitly, because it's a messy calculation. So there's no point for me going through that. So assume we have this, then Yamada reads, in this case, right-hand side is 0. Yamada reads like that. But okay, so let us have a look at, we make again some kind of funny combinations. So we look at P of L, we look at this, and this will give us, and I have to copy this, this gives us P of L plus 1 minus plus R minus L P of R. You see, I choose this in such a way that I lose one of the factors. But on the other hand, doing the calculation from here, I see that this is M1 minus L. And that was just, we assumed in this case that this is 0. Now we see if R is greater than L, then this here is non-negative. These are non-negative, these are non-negative, so everything is 0. Yeah, so because we have this kind of non-negativity condition, this gives us some rigidity, and this we push us a self in the corner. So essentially, we have in here that P has to be delta of L, and that means M2 has to be equal to L squared. So we cannot capture all cases. And then, okay, now the other part, I do it in the note, but I will not do it here. So if R is less or equal to L, sorry, it's not allowed to be L because we excluded that. Then I put the calculation in the notes. Then what I will get is that if I look at the Yamada condition, so if I look at this, the variance squared minus theta 1 minus theta, then the Yamada condition was that this is non-negative, but here I will get that this is actually less or equal to L, which is M1, so I get another condition. Yeah, so also here, so it does not work in general. Okay, but now I have trouble. Why I'm in trouble? So, okay, this is not even a negative result. This is just pointless because I choose here this particular form, yeah? But I had no reason for choosing that. Yeah, it worked in the case d equal to 1, and so I tried my luck in the case d equal to 2, and hoped, let finger crossed, things will work. But yeah, actually they do work, but you have to work a bit harder. But this is only a sign that what will happen in the case d equal to 3 and d equal to 4. And what I want to point out is if you fail in your construction, the problem is that you have too much choice. Here already you have somehow the R, which is you have 3 equations. The one for the probability, the one for the first moment, one for the second moment. You have 3 probabilities, you can uniquely determine them, but you have the L plus 1, and the R. So I choose the L, so we're left with only one free parameter R, and so this was good. But in general, I don't have to choose L and L plus 1, I could choose them also freely. So I would have 3 extra parameters for which I have no equation, and I have to wade through this kind of level of inequalities only on natural numbers, and things will get totally complicated. Yeah, and the complexity explode if I go to higher dimensions. Okay. So why I do all of this? Because I wanted to motivate you that now we have to step a step backwards and just think more conceptually out of the problem. So somehow we see that the brutal forward method, okay, I just do it by hand. I'm strong, I can do a lot of calculation, I don't care if it's hundreds of pages, will not work. So so what I have to do is, no, I have to edit first. I add a new page, which again, for stupid reason, comes unruled. And that's what we will do in the next section. So this is the section 2 of the lecture notes. I will come up with a general machine to create necessary conditions. And which will also explain my strange choices which I made before, which I could actually do because I knew what I was. I know the problem much better than I explained to you now. So I have some very clear geometric intuition what I actually have to look for, and I will try to explain you this intuition. So assume somehow I have given some moments, some putative moments. So I don't know if there are moments I want to find a probability. So assume, now we want to have necessary conditions. So we have to assume there exists a P that realize. Okay, and now I need to be a bit more abstract to formulate this properly. So what I introduce is, I don't know, if maybe, sorry, no, this is too baroque. So let me delete that. So I introduce the following symbols. So this is a vector space of all polynomials with degree less or equal to d. Yeah? Degree equal to d is not a vector space. Okay, and so an element in the space looks like that. Looks like a0 plus a1x plus a2x squared plus adx to the d. So now, can I compute the integral with respect to the expectation with respect to my probability? I mean, can I compute an expression like that? Yeah, so what I have to do, so I have two sums. So I can write this as a sum over j equals 0 to infinity, and then the sum k equal 0 to d ak x to the k, sorry, this is, we evaluate f at j, so it will be j to the k p of the j. And now what I do is I swap these two sums, and hence you can think about why I can actually do that, why this is always allowed, but let me not get too into that. So I just get this, if I do the calculation, k equals 0 to d, ak, and then I get here nothing else than the case moment of my probability. So I can compute that without knowing what is P. I just need to know that P realizes the moments. Yeah, so it's not necessary. So for all the choices, whatever you come up with your P, this will be true, and this motivates me to introduce a linear functional. So I introduce a linear functional. So you see now it goes in the direction. I meant n of f of x. Yes, thank you very much. Exactly. Here, this was f of x. What are these conditions for? Sorry, I haven't seen that. Solving the system. can you? I missed that. Okay, we can maybe discuss it at the end because I mean I think I'm already some times ago, so sorry for that. I missed that. Yeah and no, because the AKs are not negative. But you're on the right track. Okay, I will introduce the following linear. Okay, wrong color. Linear functional. So it's a functional. So okay, first I need an abbreviation. I haven't introduced that. I mean, I call this vector here, I call this M underline, just to have an abbreviation for it. So I construct this functional, which is going from the polynomials of degree at most P to the real numbers, and you probably already guess what it does. If I have a polynomial f, which is sum k equals 0 to d ak x of k, then I associate to it Lm underline of f, which is given by the sum k equals 0 to d ak m to the k. And so I reduced my interest here. Now, in some sense, I introduced linear algebra, I introduced polynomials, I used linear functionals on vector spaces. And now I want to generate a necessary condition. So, and for this, it's all of this which I'll need is actually the following very stupid thought. So if f of j is non-negative for all j in n0, then obviously I have that the sum j equals 0 to infinity, f of j, p of j is greater equal to 0. Because this thing is non-negative, this thing is non-negative, sum is non-negative. I mean, that was really difficult, was it? But you see that this is somehow about vectors with non-negative entries, and you can imagine that you have some feeling why this should be actually also sufficient. Yeah, if we wouldn't have somehow our kind of crazy kind of restrictions, it would be clear that you could pick out if a vector has positive entries or not by just taking somehow the different, I mean, polynomial which has only an homogeneous part or something like that. You could try to do something like that, but we have a bit of more complicated condition. And so this gives us essentially the general theorem 2.1. So if M is realizable, then for all polynomials non-negative on n0, we have that L M underline of f, so I have to call it f, is not 0 again. And so I get a lot of conditions in this way. So in the lecture notes, I mean, I did the different cases. So a case which I probably have to do is the case. So I do the case d equal to 2. And so I do a trick. So if I have a polynomial of degree 2, I can always write it as, let's say, something of this form. Yeah. So there's a problem with the theorem, and the problem with the theorem is actually you can also show the opposite, that this is unnecessary. And if I would, instead of n, I would take a compact set, then this would be actually, you could show that would be necessary and sufficient. The difficulty is that I have, in some sense, to classify all polynomials on the natural numbers, which are non-negative on the natural numbers. In one dimension, I can do that, and that's exactly what I'm using here. No, I have the fundamental theorem of algebra, which is coming to my help here. So this only works in one dimension. So you have to suffer more in a higher dimension, and that's where this problem actually leads into real algebraic geometry. But we're obviously not going into that. But here in the one dimension, everything is nice and beautiful. I can do that, and without of loss of generality, I can assume that alpha 0 is less or equal than alpha 1, just to make the indexing unique. Then we see, so when f is non-negative on 1, on the natural numbers. Okay, so first of all, we see that A3 has to be non-negative. It goes off to an, and if I make x very large, this thing is actually like A3 to the x squared. And if it's 0, everything is 0. That's not particularly interesting. If A3 is strictly greater than 1, then actually it is non-negative, independent which value have A3. If you think about the condition, so if I write the condition, if I write L M of f, so what that will be A3 times M2 minus alpha 0 plus alpha 1, M1 plus alpha 0, alpha 1. Yeah, and this is non-negative. If A3 is strictly positive, this is non-negative independent what A3 is. So I can assume without loss of generality that A3 is equal to 1. So this is a fake parameter. This doesn't matter. Doesn't bring me anything. Now the question is when this polynomial will be positive, and because we're on the real line, this is extremely easy to see. So if I have here, let's say alpha 0, I have here alpha 1, and the polynomial is a parabola, so it's open to the top, because otherwise it cannot be non-negative or non-natural numbers. So what I need is that the next integer, there should be no integer between the two alpha 1 and alpha 0. Now, if there's an integer in between, you are negative on the natural numbers. So the integers have to be, so it means there must exist an L such that L is less or equal to alpha 0 less than alpha 1 less or equal to L. And so I produced all the necessary conditions which I could be potentially, which I get out of my general machinery.
Hi.
Yes.
Why is not L plus 1 the rightest one?
Sorry, because I'm just mistyping.
Okay, cool.
Yeah.
And there may be a similar mistypo up in the pages, but yeah, never mind.
Thanks. No, but this thanks. Yeah. So I cannot have an integer in the middle. So we see that there's still a lot of conditions. No, I mean, we have the only is we can have arbitrary two numbers so long they are somehow lying between two integers. And what you can show, and that is one of the exercises, you may think, if you look at this picture, you may think the best thing you can do is you push alpha 0 to L and alpha 1 to L plus 1. No, that's, which is somehow, I mean, either you can make them equal and you can hope that that's somehow the most important case, but that's not true. This will just give you the variance is non-negative. Or you may think that, okay, making them as wide as possible would be the right thing to do. And that will give you actually what we had before, because then we actually boiled back to the case I did a special case in L where the things fall from the sky. Now that was my choice. In the previous thing was exactly to say, okay, yeah, the best thing is they go both to the maximal value. And that's the exercise I left for you, is to show that actually the Yamada condition implies all of these conditions. Now the conditions are not negative. You have a lot of them. The interesting thing is you actually only need one of them. Yeah, you have a lot of them. You only need one of them, and that's a clever choice for L. Now I gave you this interesting argument. Yeah, this is very easy to understand because I just push the alphas to the maximal value. The polynomial will go down. You see this in this picture, and that's clear why that, yeah, but then that's somehow I'm screwing up in the next exercise. In the next exercise, I just show you, I just ask you to show that if you fix L, then if you have fixed L, then it is not the best choice to have alpha 0 and alpha 1 equal to the maximal values. It's only if you leave alpha 0, alpha 1, and L all simultaneously free that you have to choose an equal and then the L optimal. So it's non-local, yeah. So it looks very appealing, but it's not what it is like. So, but I will, so a new page after. Okay, so that's now I'm in time to formulate the general condition, and for this I have to introduce some notation. So introduce alpha d, and the alpha d's are it's a set of d tuples. These are the zeros of my polynomials. So the polynomials, I want to consider polynomials which have d zeros, and I have alpha 1 is smaller than alpha 2. They're all different, smaller than alpha d. And then in the case if d even, then I want that alpha of 2, I have to copy that because it's so, I always screw this up. I paint you the picture. The picture is easy, the formulation is difficult. So this is an alpha 2k for k equal 1 to d half, and if d is odd, then alpha 1 is equal to 0, and alpha 2k plus 1, sorry, now I screwed it up. So this alpha 2k1 plus 1 is alpha 2k, and here in the first one is alpha 2k is equal to alpha 2k plus 1. So the 1 plus. Okay, I can never remember that, but okay, I'm gonna give you a picture. So d even. So I have my integers here. So then I select pairs of neighboring integers, and I look at a polynomial which looks like that. You go here, this goes under, this goes up. This should be a nice convex behavior, and goes up like that. Yeah. So the zeros comes in pairs of neighboring integers, and in the case d odd, the picture looks slightly different. It's the same idea. So this is exactly the idea that I push the zeros as far out as I can. So let's assume this is 0 here, 0. So zack, zack, zack. So I have to have 1 0 here, and let's say another pairs of 0 here, and then I look at a polynomial which goes like that. I go up here, I go down here, and up here. Yeah, and they're obviously polynomials which are non-negative on the integers. They look very appealing because they're the one somehow where I push the zeros as far out, as far apart from each other than I'm able to push them. Okay, so because then I define, so the I forgot to say this, the polynomial f alpha of x is defined as x minus alpha 1 times x minus alpha 2 times x minus alpha d. So, and with PD, so script PD, I makes a collection of all of them. And these are exactly the polynomials which are non-negative on the natural numbers of degree d and which have exactly d distinguished zeros. You can think about that. I give you in the lecture notes some hints how to see that. And so this lead me then to the following theorem. So theorem 2.4, if M is realizable, then I have that L M of F alpha is greater equal to, or F is greater equal to 0 for all F of polynomials of the above form. Yeah. And now I think it's time for a break. Then in the next lecture, I will give you a small insight in a theorem which I will need, and then I will try to explain you how actually to see in which sense or what I have to add to make this condition actually sufficient. So
Thank you, Tobias. I'm going to stop the recording.